All right, thanks for coming to this talk. I know there's 2 tracks going on, so thanks for your time. I'm super excited to be here to tell you guys about Ethereum. This is something I'm very passionate about, very excited about, and I'm just happy that I could be here, and hopefully you'll learn something. So we're going to talk about Ethereum. We're going to start from 0 and go all the way to Go all the way to the most technical things, including the virtual machine and sort of like how contracts are actually executed. So let's dive right in. I co-founded a team called Prismatic Labs. We're a team of independent blockchain developers, enthusiasts, hackers. We're not affiliated with Ethereum directly, but we work with the foundation to help build the proof of stake and sharding protocol for Ethereum 2.0. We're 6 people today, hoping to grow soon, but we're a research team, implementation team. We kind of started this as just like a moonlighting project, something we were really excited about, and then within a year we had all quit our jobs and now we're working on it full time. So it's a really exciting space to be in, and really anybody can be a part of it. So let's go right into it. Starting with the fundamentals, like what is a blockchain? So before we even go there, we need to understand what is a hash function. So all you need to know about a hash function is that we can take some input of variable size and deterministically generate an output of fixed size. So on the left here we have some hash function. It's not important what it is, but we take the input fox and we get this hexadecimal string that comes out the other side. Same thing with another like longer phrase. The red fox runs across the ice, generates a completely different input. And if we tweak this phrase just a little bit to say that the fox walks across the ice, we should get an entirely different input. It's not slightly different, it's entirely different. And this makes it a really powerful tool because it's a unique identifier that uniquely identifies this input to some output. Another important thing to know is that this is a one-way operation. We can't take this hexadecimal string and determine that what the input was to generate this. It's only one way. Now on the right here we have an example of a bad hash function. The inputs need to be unique based on the outputs need to be unique based on the inputs. So here we have some names. Imagine these are like usernames or even passwords. And we run it through the hash function and everything is great, but then we see that at the bottom Sam Doe and Sandra Lee hash to the same value, and this is really bad because maybe this is how we were doing our access control. It means that both of these users have access to the same account, which is a big problem. So that's a bad hash function. Now moving on, so how does this relate entirely to blockchain? Well, blocks are basically these arbitrary sets of data that have a reference to the previous block, and they're linked together that way in such that it kind of resembles a chain. Your chains are links all in a row, and they're based like this, and they're always growing. So here we're starting at block 100, and block 100 has a reference to the previous block, block 99. Because we have a good hash function, we have this identifier that is unique to block 99. And so on the next block builds on top of that, has a unique identifier to block 100, and so on. And this grows over time. Now something important to notice is that the arrows are pointing backwards because that's how it works. They don't have a reference forward, they have a reference back. So when we're at block 103, we don't know what block 104 is going to be, so we don't have a reference that way. The arrows point backwards and time goes on. If you're a developer, you may have been using a blockchain all along, something called get version control. This is what is very common for people to use when they're working on teams in parallel with other developers, working on features. We have these things called commits, so we're committing our changes to the project, and each commit has a reference to the previous one. So based on that definition, this is a blockchain because it has hashes reference to the most previous commit. But something to think about though is that get uses a hash function called SHA-1, which has been very famously broken by Google a couple years ago in an attack called Shattered. And with enough computing resources, 110 GPUs, you can find 2 different inputs that hash to the same output in just 1 year. So that's actually a really small amount of time for an attack like this. If you just had 10 times as many computers, I mean, you can scale that time down very quickly. To put it into reference, that's still a lot of like comparisons. It's 9 quintillion comparisons to find a hash collision. So it's still like pretty good for your like school project or public open source project, but something to consider. Don't use Git for your cryptocurrency blockchain. It's not going to work. So bring that together. What can we use blockchain for? So the most common one that we'll hear today is Bitcoin, the decentralized ledger. So this is taking this ledger, which is a list of transactions, accounts, account balances, has no central authority, and it's cryptographically secure. So as long as you hold your keys, nobody else can move your funds around on your behalf. So plugging that in, the arbitrary data that is on Bitcoin are transactions. So these are operations on the decentralized distributed ledger. Now what we take away from Bitcoin and the founders of Bitcoin is that we really get these 3 amazing properties that didn't really, they all existed before, but they never came together in such a way that empowered us to have cryptocurrency and decentralized application platforms. We have this concept of running a database across thousands of nodes or thousands of machines all across the world where nobody knows anybody. It's pseudo-anonymous, and that's a really powerful concept. We haven't had that before in this scale. It also introduces a peer-to-peer payment system, Bitcoin itself. That's unique to Bitcoin. We haven't seen that before. Having peer-to-peer money where we don't have some third party to transact, to authorize it, is a really powerful concept. And then finally, the most exciting thing in my mind is the crypto economics of everything. So how do we design this system such that people are incentivized to behave appropriately? That's pretty cool. But that's, to me, not as exciting as Ethereum. So let's dive into the real juicy stuff. What is Ethereum? What is this crazy thing? What can we do with it? In short, in one sentence, Ethereum is a decentralized application platform. So we can run applications on a global set of computers in an unstoppable, immutable way, and it's, it takes out the need for some third-party trusted source. We can have these trustless applications. So let's take a look at, what does decentralized mean in a visualization. On the left, we have this central authority where everything has to go through them. Imagine this is, Venmo is a good example. When I send a transaction through Venmo, I send it to their server, and they, check it, it's okay, and then they forward along the transaction to the end user. If for whatever reason Venmo doesn't like me, they could stop that, they could censor it. It's centralized in that way. But if we have this peer-to-peer system, everyone's talking to everybody. There's no central authority. There's no single point of failure. So that's a really powerful concept. So let's take a look at some use cases. Starting with the most obvious one, the underlying token of Ethereum is called Ether. It's a cryptocurrency. It's a commodity. It's a store value. It enables these borderless transactions, so we can send money anywhere in the world for a couple pennies. It's really cheap and fast, and it's borderless in that way. We don't have to, if you've ever tried to send money internationally, it goes through all these steps. It takes days. It's complicated. It doesn't make any sense. And the scariest part about sending a wire is the example. The scariest part about it is once it goes out of the door from your bank, they don't even really know where it is exactly. It hops from bank to bank, and it's just kind of scary. Where this is, we can see exactly what's going on. There's just one confirmation to see it. It just has to be included into a block. So it's a really powerful powerful concept for enabling these kind of, enabling the people who either don't want to or can't have bank accounts. Another thing we can do is secure agreements. So if you've ever used a product like DocuSign where you're digitally signing some agreement, you know, through DocuSign there's still this central authority where DocuSign was the witness and they have a copy of that data, but you could do this in a decentralized way where we can all agree to, or the two, in this case, two participants can agree to some agreement and then commit that onto the blockchain. The blockchain is this immutable space where nothing can be manipulated or reverted or erased. But you can also use a concept called zero knowledge proofs, which is a way to commit this agreement to the blockchain without revealing the conditions of the agreement. So maybe we want to reason about that I have at least $1 million in the bank, but I don't want to tell you exactly how much money I have. With a zero knowledge proof, I can do something like that. So likewise with this agreement, we can reason about an agreement without having to reveal all the details. So that's, you know, and that's backed by cryptography and math, and it's also a really powerful concept. The next thing you can do with Ethereum, and this is kind of the biggest use case I think so far, is that you can create your own tokens. So instead of having to launch an entirely new blockchain, you can create tokens on the Ethereum blockchain that are, you know, fungible, where there's many of them and they're not unique, or you can have non-fungible tokens, which are like collectibles. You can also have things like security tokens. So if you're a major company that trades on like a stock exchange, you could think about how you can sell or put stock ownership on the blockchain. You can put like property ownership, so like your car, your house, or your racehorse or whatever. Collectibles like this crypto kitty here, but also utility tokens. So if you offer some kind of like platform as a service or anything where you issue credits, so like if you imagine like you have to buy credits for some online service, well, you can make these credits in the form of a utility token where users can actually, you know, give credits to their friends or whatever, and it's all in this decentralized way. So that's pretty cool. Another unique concept to blockchain is having the idea of a decentralized autonomous organization. So this is a company or a group that doesn't have a CEO. It doesn't have someone who's in charge here. So it's a group of people who can use their tokens to do on-chain voting or governance and kind of make decisions about what the company or group should do. There was a really famous one on Ethereum called the DAO, and it was really famously hacked. But before getting to that, we'll talk about what the mission of that was. It was supposed to be like a decentralized venture capital fund. So everybody in the community was putting in money and getting DAO tokens, and they can use these DAO tokens to fund projects on Ethereum that benefit the greater good. And that was a really powerful concept because you couldn't trust all these strangers to come together and then elect a stranger to then decide where all the money goes. It had to be in this decentralized way, so that was really cool. But it was hacked. A hacker was able to drain all the money out, and we had to do what's called a hard fork to undo that, and it's the only biggest one that's ever happened and will never happen again because it was quite controversial. So, interesting concept, but if you're going to do this, just be careful not to mess it up, because on blockchain it's immutable. You can't go back. You can't change the rules. So that's pretty cool. Another use case is, you know, Ethereum is a decentralized application platform. You can use underutilized resources that are running on all these machines. So you can do things like training your machine learning models, or evaluating the models, or doing video encoding. So like a decentralized YouTube is a cool example, or just like really anything that you want to run somewhere that's not your computer or doesn't fit on your computer. So pretty cool. Another exciting thing or really interesting thing was this game called FOMO 3D, which is, FOMO stands for fear of missing out. And the way this worked is there was a contract deployed that for every key that you would buy, it would extend this timer, and for every person that owned a key, when a new key was purchased, they would receive part of that funds, and the rest of it would go into this like jackpot. And the whole point of this was that the price of the keys would increase every time. So if you got in early, you were going to start earning passive income until this timer went out. But if you were the last person to buy the key when the timer ended, you get this huge amount of money, which was, I don't know, tens of millions of dollars when it finally ended. So it's a really interesting concept and a very intriguing game. There was actually a lot more to it. You could have like, you could choose a team, and there was like airdrops and side betting and just like all this crazy stuff. And that was really cool. I think it was last year. Decentralized exchanges. So when you're buying cryptocurrency or exchanging cryptocurrency, typically you have to go through some exchange, so something like Coinbase, but you don't need to, right? So we can build these systems where we can do these trades on chain. There's no trust involved. There's no third party we have to think about. There's no like KYC, know your customer, or AML, or any like identifying information there. We can just go to a platform like Uniswap, which says, I want to trade 1 Ether for some DAI stablecoin, and you just swap it with somebody. It's all anonymous. It's great. The biggest thing in the space right now is a concept called open finance. We've been talking a lot about transactions and the risks of using central authorities and things like that. So if you're looking on the left, when people want to interact with businesses to send money, right, they have to then ask the payment processor. So when I go to the grocery store and buy groceries, they have to ask Visa, hey, is this okay? Visa has to say to your bank, hey, do they have the money? The bank has to, check with the federal government that this person doesn't have like a freeze on their account or anything, and all of this is backed by gold, supposedly. So taking open finance onto Ethereum turns this pyramid upside down, where we start with the trustless asset. We start with the store of value, Ether, and then we have these like permissionless banks and permissionless lending, and all these financial instruments and applications that can be built on top of it. So that's a really powerful concept, and there are a lot of projects doing that, so it's a really exciting space to be in, and just like a really cool thing going on right now. To me, though, the most exciting thing that I can think of is something that hasn't been thought of yet. I left out a lot of use cases here. I'm sure you can imagine some of your own, and I encourage you to investigate this, see what you can do to take something that is centralized and evaluate, does it need to be centralized, and if not, you can build it on Ethereum blockchain. So now that we know sort of like why we might do this and sort of what it is, let's talk about how does it work exactly. Let's get into a little bit of the details. It's complicated is the short of the story. So this is a really busy slide, and we're not really going to look at it for very long, but I want you to just take it in that there's like a lot of pieces to it, where Bitcoin is relatively simple. Bitcoin's still complicated. Having Ethereum do application processing and virtual machine computation is a lot more complex. So let's go ahead and dive right into it. Starting with the most basics, we have these things called transactions, right? And a transaction consists of a destination, who we're sending to, who it's coming from, a nonce value, which is just a unique identifier starting at 0, a value, how much we're sending, any kind of data, so if that might be if we're interacting with a contract, we might send some data. Then we describe some gas price and gas limit. We'll get into that in a moment. But here we have an example. We have this, I don't know, he's like a farmer, and he's got his keys to his wallet, and he wants to send this fireman, maybe he put out the fire on his house, he wants to pay him for that. So he's going to send him 3 Ether, and he's going to pay 7 Gwei for the gas and sign it, and that goes out to the blockchain. And when it gets mined into a block, the farmer's balance is reduced by 3 Ether, the farmer's balance is increased, and the miner gets the gas fee. Another thing they can do is they can deploy a contract, so they can deploy their own application to the platform. And the way they would do this is they send a transaction with no destination, and it has contract data. So they just send that out there into the world. It gets picked up by a miner, and a new contract is initialized at this address. One thing to notice, the nonce is increasing every time. That's important. Increases again, and then we can interact with our contract, right? Maybe this was one contract I deployed recently is I wrote a birthday card for my friend, and inside of it, it had $20 in it. And on the birthday card, I had written a secret passphrase that I had hashed, right? The hash is a one-way operation, so it was not public that way when I deployed it. But they could write the password in there and take the money out, and they could have this birthday card on the blockchain, and it had a note in it, and it was super cool. You can imagine maybe that's what this farmer is doing here. Let's talk about the contents of a block. Most of the fields in a block are metadata describing the state that came before this block and the state that comes after processing it. So we have the parent hash, that's the reference to the previous block. We have this concept of uncles or ammers, which are like blocks that were built around the same time, but on a weaker chain. We'll actually include them back into this chain, and both parties get rewarded a little bit for that. A beneficiary, so this is the miner. So with every block that's mined, there's some reward that goes to the miner. So here they'll define where they want that to go. Logs bloom, this is, there's a bloom filter for the logs that are emitted. So this is like the root of that. A block number, these are increasing every time by 1. We have some information about the state, so there's a state root. We'll get into the state in a little bit. Receipts, transactions, timestamp, self-explanatory. Difficulty, that has to do with mining, we'll talk about that. Gas, extra data, so you can actually write, you have a field on a block where you can write anything. You can write your name. If you're the miner, you could write a fun note. You could just write, I don't know, whatever you want to. And then you have a mixed hash and a nonce that has to do with proof of work. But the bulk of the content in the data is the list of transactions. It looks like it's not, but it is. I mean, there's just a lot of metadata and then a really long field, a list of transactions. So the state, as I said, is, you know, in Bitcoin, it's just accounts and balances. Here we have accounts. There are two types of accounts. We have externally owned accounts, which are something that I hold the key to or you hold the key to, and then we have contract accounts, which no one holds the key. We just deployed that contract there. It lives there, no one controls it, it's there forever. We have account storage, so you might think that that birthday card I had a note in it, that's account storage. We can manipulate that storage through the API, through the contract. Maybe we're changing the node, or you know, if it's the FOMO 3D, we're buying more keys, so we are allocating keys to people. And then in the state, we also have transactions, and then receipts. The receipts are the in-between states of processing transactions. It's basically this hard drive that powers this world computer of Ethereum. And this is kind of what it looks like all together. Without getting into too much of the details of what a tree is, I know it looks like it says try, but that's short for retrieve, so it's a tree. This is just a way that we can represent this data so that when we have changes, we don't have to include the entire data object. We can just include the top of it, and that's enough proof for us to reason about changes that are happening in these data structures. So we have the world state, which is just accounts and account storage. Then we have receipts, which we talked about are, you know, the in-between states of processing transactions, and then transactions themselves. And that's kind of how it all fits together. Right, so the thing that powers Ethereum or that powers these contracts are the code execution. So we have these things called smart contracts, and here's a picture of one on the right. This one is a voter ballot. So I can cast my vote on a particular candidate. This one is this is a chairperson, so we can vote on that. And this is run inside of a virtual machine. So when we compile these languages down, we compile to a specific machine code that is understood by the Ethereum virtual machine. All the operations will be the same. It can run anywhere that runs the virtual machine. The important thing to know about contracts is once they are deployed, they cannot be changed. You cannot modify the code. That's really important for having a trustless environment because we know that once the rules are set, that they're always going to be that way. And this supports multiple languages. Here we're looking at Solidity, but there are a couple of different languages out there, one called Viper, which is kind of like Python, if you're into that. And there are more details here if you look at Solidity's docs or go to ethervm.io. There's a lot of info there. Here it is all pictured together. This is too much to look at. I mean, it's too early to look at this thing, so we're going to skip over it. Gas. So I've been saying gas a lot. What is gas? Why do we need it? First of all, we need this because when we come up with there's this kind of like tragedy of the commons problem where if we create this public good and it's free, it's going to people are going to find some way to misuse it or abuse it, and kind of like to the detriment of everybody else, we don't get to have this nice thing anymore. So we have to enforce gas, where people have to pay for the things that they're doing. If you're running some expensive computation, well, you're going to have to pay for that. If you're going to send a transaction, well, you're going to have to pay for that. We can't have nice things. It can't be free. So gas is just a computational unit of how we pay for things. We pay for gas with Ether, and the price of that determines how much Ether we're going to pay. So every transaction starts with a minimum gas requirement of 21 gas units. And then we're going to pay for every operation. I said that contracts are compiled down to machine code. Machine code is just, basic. You have your like arithmetic, so adding things together, dividing, and storage, and all these other things, comparisons, right? That's all programs are anyway. We're going to pay for every operation, where storage costs the most. So since storage costs the most, we bring back this idea of crypto economics. So how do we incentivize people to clean up after themselves? So we'll actually give you a refund if you delete your storage after you're done with it. So that's pretty cool. The gas that we pay is paid in ETH, and that goes to the block producer, the miner that produced this block. Let's talk about proof of work. This is what drives the whole thing that keeps it secure. We have a block here with the header. This is in pink or purple, whatever color it looks like to you. And it has all this metadata about the state pre and post of this block. We take that and we run it through an algorithm called ET-hash, which is just some cryptographically complex puzzle that a machine has to solve. And they do this over and over again until they meet some difficulty factor. So if you can imagine, we have this hash function, ET-hash, and it comes out with this hexadecimal string. And we could define our difficulty as if this string has 5 zeros in the front of it, then we've solved the difficulty. And that is, probabilistically difficult because the hash function is random. It generates this like random output. We can't predict what's going to happen. So that's proof of work. So taking a look at ETH-hash, it's different from the hashing algorithm that Bitcoin uses because we're trying to defeat what's called ASIC chips. So these are manufactured chips specifically for certain types of hashing algorithms. So if we're using like SHA 256, well, that's going to be, I can write a specialized chip that's really, really fast at that. And if you're a manufacturer, you have an advantage over everybody else because you can choose not to release this hardware and run it yourself. And you're mining blocks faster than everybody else. You're getting the reward faster than everybody else. That's an unfair advantage that can make the system more centralized, where you have these, big manufacturers colluding together to come up with the biggest mining farm. So we come up with this algorithm ET-hash, which is ASIC resistant because it relies a lot on your memory speed. And memory speed is something that's really, really hard to manufacture. We kind of all have the same memory speed here. So it's like usually people use graphical processing units, which are really good at this kind of thing. But the quick details here are that we have this directed acyclic graph, which is just a lot of data in a graph where there's no loops. And we iterate through this graph running the mix hash function over and over again until we've hashed every single page in there, and this is growing. So that's another way that we defeat the ASICs chips, is because if you try to develop a chip with this specific graph, well, the graph is always changing, so your chip's going to be useless as soon as the graph changes. So it's every like 5 days. Okay, so talking about the future of Ethereum, this is what I work on and what I'm most excited about, Ethereum 2.0. We're only going to get into it a little bit. We're not going to dive into the details here. There's another talk later in the workshop room where we'll dive into details and kind of get hands-on and look at the testnet. So I don't recall the time of that. It's in the afternoon, so just check the schedule for that. But first of all, why do we need this? If we just described this like really amazing, really powerful tool, like why do we need another one, another iteration of it? Well, Ethereum is only about 12 transactions per second. And if you think about like what does Visa do or what do these other payment processors do? They do thousands of transactions per second. So we're not anywhere close to reaching a global scale that could, you know, potentially displace these kind of technology. We're super far from that. So we need to come up with some scaling solutions. We also have a 14-second block time, which means at a minimum you're going to be waiting 14 seconds for your transaction to be confirmed. But usually you wait at least one block. You have to wait for the next block to be mined for your transaction to be there. And on Bitcoin, that's 10 minutes, so it's even worse. Proof of work, the thing we just talked about, is very energy expensive. You can imagine people are running these like warehouses just full of computers, just generating heat and running through these algorithms and just basically wasting a lot of energy to keep the network secure. Like it's a valuable thing, but we can do better. So we can introduce this concept of proof of stake, which is a lot more computationally efficient. And all of these things together are going to enable a decentralized future on like a real, truly global scale. So what is Ethereum 2.0? That's what it says. It's a little covered up, but this is the founder of Ethereum, Vitalik Buterin, and he says Ethereum 2.0 is a big multi-year-long upgrade to massively increase the blockchain's scalability with sharding, increasing security with proof of stake, and improving programmability with fixing a bunch of things we got wrong the first time. So rewriting the virtual machine. So what he's describing here is rewriting everything. So we're starting over everything, all the code, we're redoing everything. We're introducing sharding, which is a form of horizontal scaling. It's popular in database architecture. We're introducing proof of stake, which is another way to reach consensus. And we're changing the virtual machine, which is how everything works. So with that, I want to leave you with this. Ethereum is an open community. It's built by people who are just passionate about the project. I don't work for Ethereum. Very few people actually work for the Ethereum Foundation. Most people in this photo, this is a photo of a lot of people that are involved in the core protocol, involved in Ethereum 2.0, Ethereum 1 as it is today, all coming together to talk about, you know, the future of Ethereum and how we can build this together. So thanks for your time. If you have any questions, I think we have a microphone. Thanks.
Hey, thank you for that talk. I have a lot of questions, but I'll just ask a couple. So first, I've tried to understand what DeFi is, and I still don't think I get it. Can you explain that a little bit?
DeFi, so decentralized finance, it means a lot of different things. So it's kind of like a wide ranging term that kind of casts over anything that's like financial product or financial derivative. So we can think of things like a stable coin as part of the DeFi space. So coming up with something that, some sort of token where one token represents $1, and that reduces volatility. It's a really great improvement on the whole peer-to-peer payment system because we can expect, you know, the value is going to be the same when they get it. But also things like lending, those are part of the DeFi space. Yeah, I mean, does that answer your question?
Yeah, thank you.
Sure. Yeah.
And then, another one, you talked about that hack where you then had to do a hard fork.
Oh, the DAO, yeah.
Is that something that should concern people down the line? Like there's always going to be like someone that has the capability of like essentially changing the immutable blockchain?
Yeah, so that was a really controversial event where the community was basically divided on this. The hack was so detrimental that it compromised, I think, like 20% of all of the tokens that existed. And to give one individual to hold that kind of currency gave them this power that they can really like break the whole system. So the community came together and decided that we should do a hard fork and refund the money back to the participants of the DAO. But the argument against that is it really immutable if we can all agree that it should be changed? So there's like both sides to it. There's like some camp where they say, oh, the code is a law and we can never change it, and that was stupid, or why'd you do that, and it's a scam. And those people tend to prefer, Ethereum Classic, which has like, really good virtues, like code is law, and that's what it should be, and that was the original intention. But then you have people on Ethereum which says like, we want this project to survive and it needs to go through upgrades, and these things happen. And this one was a rare exception that there was so much at risk that I think it made more sense to fork than to have this like potential actor that's holding so much of the total supply. It would have been too risky to continue, I think. Great question.
Thank you for your talk too. And my question was, since these platforms and like this currency is based on like a centralized monetary currency, I guess, which is dollars or US dollars, for example, if something were to happen like the last speaker told, like inflation or something like that, like the value of the money goes down and stuff like that, then as a consequence, the cryptocurrency, even though it's another currency, like it will still be affected by what happens to the US dollars, right?
Yeah, I think so. So there's a lot to unpack with that, is that these markets all tend to move together. So you see like when Bitcoin goes down, or Ether goes down, and all these other coins go down, and the inverse, everything seems to be moving together. And I think there is some correlation between the like fiat markets and the cryptocurrency markets. I'm not an economic person, so I don't, like economist, so I don't really know, I haven't studied that too well, but I've definitely noticed that trend that like if the stock market is particularly under stress, then you'll see some movements in the cryptocurrency space as well. Does that answer your question? Okay, thanks.
Just for clarification, it was an exchange that was hacked at that time. It wasn't the blockchain being messed with itself, or was that dev?
It was the smart contract that represented the DAO. So the way the hack worked is that anybody could join the DAO, right? And anyone could be a part of the decentralized autonomous organization. But if you wanted out, you could withdraw your funds and get out. Well, the hacker was able to find what's called a replay attack, which means that they could replay the same interaction before it's completed. So they would call withdraw and call it 10 times in the same transaction when they were only supposed to call it once. So with this, they were able to deposit, withdraw, and they continually just drain out all the money to another DAO that they had created. And there was like a 28-day, like there's like a lockup period. So they didn't really get all of the money before it was detected, and they were able to stop it. But it was an on-chain hack, like the contract was hacked itself. It wasn't an exchange, it was the contract.
Okay, thank you. And one last question.
Sure.
That's a little more specific. You're obviously a little closer to the Ethereum scene or whatever.
Yeah.
Do you know what they're planning with 2.0? Like how many ETH is going to be like the minimum for staking? Or is that still to be decided?
It's not final until it happens, but the number we're considering is that for one validator to be one participant, it's going to be 32 ETH. and the total required to start the system is around 1 million or maybe 2 million. It's like specifically 16,384 validators. Is that what you're looking for?
Yeah, exactly.
Okay.
Thank you.
Yep.
Can you again explain the relationship between ETH hash and the manufactured chips? I kind of I misunderstood that.
Yeah, maybe it'll be helpful if I go back to the slide if I can. Right, so in a manufactured chip, in like step 1, where we can do this like SHA function, this can be optimized on the hardware level on a manufactured chip. This is specifically designed to run with this particular hash function, where it's like it's a constant function. But with ETH hash, the hashing function changes dynamically, so it's not always like run the function this way. It has some like parameters to it that change based on this graph. And the graph is constantly growing. So even if you were manufacturing a chip for the graph as it is today, it's going to change in 5 days. So there's not really an incentive to do that unless you can manufacture chips really quickly. But even then, like, how fast can you do it? So does that answer your question? Okay.
So you mentioned there's an issue with efficiency that you guys are working on.
Yeah.
But then you talk about this ASIC resistant, capability. It kind of sounds like a contradiction, right? Like you could design chips that are more efficient. Obviously, one manufacturer would be more advantaged, but how do you kind of wrestle with that sort of paradox there?
Yeah, so the trade-off we make here is that we're encouraging a more decentralized space with the ASIC resistance. And I think maybe the energy costs are pretty similar. But yeah, I think like from a manufacturing standpoint, it's probably harder to find like more energy efficient graphical processing units, because those companies are typically targeting gaming users and like video encoding type stuff, and this isn't really their target audience, although they did enjoy a lot of the sales from these kind of things. But yeah, I think that's really the trade-off, is like we prefer to have a more secure and decentralized algorithm than something that's like can be optimized for efficiency, because that was the first goal, is security and decentralization. And that's kind of like the really hard part of this trilemma. Like how do we write Ethereum 2.0 where it's decentralized and secure and efficient? Like it's pretty hard to do. So thanks for that question. How are we on time? Okay, so we still have time for more questions.
I'm just curious. So how is Ethereum 2.0, if it's like starting from scratch, how is it going to affect the projects that are already on the current Ethereum blockchain, or are they going to be able to like migrate, or how is that going to work?
Yeah, so there's a migration path. The exact details are still in active research, but we can imagine that there's an opt-in path where you can migrate your data over early into what's called an execution environment. So we're like, this will come out a lot of details in the workshop later, but when we have these different shards, they also have what's called execution environments, which is using the new virtual machine. So we can copy the state over from Ethereum 1 into Ethereum 2 and kind of populate this shard with the existing state data as a migration path. So you can imagine that when we're like, Ethereum 2 comes as another blockchain running on the side. And when we're ready to sort of break the connection between the two, we'll take a snapshot of Ethereum 1 and populate a shard with this state data. So this brings over all the contracts, all the account state data and all those things, and then sever the tie between the two. And so that's like the big migration where you can't opt out of it. So now if you didn't migrate, you have balances on both, which is kind of complicated, but for like tax reasons. But that would be the point where we're doing like migrating everything. So that's sort of what you're looking for. Your question? Okay. Yep.
So earlier you mentioned that Ethereum is essentially a decentralized application platform.
That's right.
So if I were to want to create a decentralized server on your Ethereum, how would I go about doing that?
A decentralized server?
Yeah, so like it serves a domain or something like that.
Yeah, so we can think of Ethereum as the decentralized server, and if you wanted to, like maybe like website hosting, is that what you're looking for? Yeah. So the data that we can write on Ethereum is you pay for it once to write it there, and you can read it infinitely for free. Everyone has this data around, and it's free to read. You just have to find some way to serve that to like the World Wide Web, and that has to do with like DNS routing and all these things. So we actually have, like if you wanted to do website hosting, I would encourage you to look at a project called IPFS, which is the Interplanetary File System. And this is a decentralized file store where I can upload my files and they can actually be served on the web and act as like a server in that sense. But if you wanted to do some like on-demand like processing for end users, like in real time, well, blockchain's kind of not at that level yet because there's this 14-second delay for blocks. So using a website, like if I was like logging in or like changing settings in my account on a blockchain-based application, it would be a noticeably slow experience. So we're coming out with ideas called like layer 2 solutions, which are this like layer above the protocol, so that we can make these fast like reads and writes, and then periodically like commit them to the blockchain. So there are like solutions around it, but when you're thinking about how do I deploy my thing, like Ethereum is the server, and you're kind of just deploying your application, sharing resources with everybody else.
You mentioned with a smart contract, once you deploy the code, you can't change it.
Right.
What if you have mistakes in the code?
You're gonna live with it. I mean, that's just, not always, right? So there's this concept of upgradable contracts where you actually have a proxy in the front, and the proxy can define where the backend is. So if I deploy version 0, because we start at 0, the proxy will have just be a pass-through to that contract. And if I want to upgrade it, I can just change the proxy to point to the new contract. And so that way I can have this concept of upgradable contracts. But if I deployed version 0 with a bug, like it's always going to be there. There's not really anything you can do about that. So the important thing is to like really carefully audit your code, and for security reasons and also just for like logical reasons. Formal verification is like a great process to do. So it's hard because blockchain's like a really unforgiving space, and users will learn that very quickly, that like if you lose your keys, no one's going to help you get them back, they're gone. Likewise with contracts, like if you write a bug, like you're pretty stuck with it. So.
Hi.
Yep.
Back here. So if I create a token and I want to have an app that functions with that token, do users still have to pay gas fees with Ether, or how does that work? How do I eliminate the use of transaction fees or gas using my own token?
Right. So if you have a token and you want to interact with it on the Ethereum blockchain, you have to pay gas in Ether. And this is something that people have often been confused by, where they're buying their like favorite, maybe they're investing in some like ERC20 token, and they've only bought that from the exchange, and when they try to take it out, they realize they need Ether to move it around, and it's kind of like, wait, why do I need this thing? So we're working on better solutions for that. There's really like two ways to get around it, is that you can do these transfers in like a layer 2 protocol, which is layer 2. It can be something like side chains or state channels, where like you kind of define your own rules, and it's semi-centralized, where like there's an operator of it, but all of the rules are enforced on the blockchain, so they can't really do much. Like if they were to become malicious, they can't really do much. And since I've defined my own rules, I can say, oh, you can pay for transfers with with that token, the underlying token, and we'll reconcile that on the blockchain for you. The other thing is that we're thinking about in Ethereum 2.0, there's maybe an opportunity that these different execution environments can have different gas markets. So paying for gas in different assets is an idea. It's still in active research, so I can't guarantee you that's going to happen, but we understand that's a friction for a lot of people. Great question. Yep.
So are you familiar with the Open Zeppelin gas station network? And if so, do you view that as sort of the future to improving the user experience of decentralized applications?
I'm not familiar with it. Sorry. Okay. Do you want to describe it, and maybe I can talk about it?
Yeah, it essentially allows for a third party to pay for the user's gas fees, so that there's no need. It basically eliminates the need for MetaMask and for the users paying to interact with the smart contracts.
I think it's a great idea. I haven't looked into it too much. Obviously, just hearing about it now, but I think that's going to be a great way for user adoption, because that is friction for people. It's like, why do I have to pay for gas? Or what is gas? Like, it's still, maybe even today, some people are confused, like, wait, what is gas? Like, is it gas or is it ether? Like, what's going on? So, yeah, I think we need to work on that, and that's being worked on. Yep. Another question here, yeah.
So other than the way that the platform manages the transaction, like what would be the difference between like just transferring money through Venmo and through through Ether, for example? Because I'm paying Venmo to use my money in the bank account to transfer to another person. Here I'm paying Ethereum to basically do the same thing in a different way, but I'm not seeing that, you know, like, my goal is accomplished both ways in the, you know.
Yeah, it's true. Like, if the only thing you care about is like, does the farmer receive the money? Like, sure, like Venmo would work and this would work, but the power is, what if the farmer doesn't have a bank account, or if they can't have a bank account? What if they live in a country that's under high volatility, where like their currency is unusable, or Venmo's banned there by state entities? Like, you can't rely that these things are just going to work. Like, not everybody can take Venmo, but on a thing like this, like, you know, it's can't be. It's not permissioned, right? It's trustless. Like, we don't need this third party to get that there. So it's not perfect for like every use case. Like, if you really just need to send someone money, maybe Venmo is better. But I think that this is like the way forward. Once we get to the usability level of Venmo, that having it on a blockchain is going to be really powerful. I think that's it for questions. Thank you guys very much. Have a great rest of your day. I'll see you at the E 2.0 thing.